Good afternoon, everyone. In this session, we are going to cover Runtime Security Engine and its evolution. Myself, Shibu. I'm the technology manager for RSE firmware, and I'm joined with Rafe today, who is the RSE firmware architect. RSE or Runtime Security Engine is a Cortex-M based security subsystem, which is getting integrated to various ARM-based solution over the last few years across market segments. One of the primary questions to ask here is why RSE when there is already security solutions in ARM. So if you look at the application processors, there is already TrustZone, which enables a trusted execution environment on the core itself. At the other end of the spectrum, there are the TPM. We already heard various talks related to TPM. One of the primary drivers for RSE has been the ARM confidential compute architecture. So as part of the ARM CCA threat model, there's a requirement to have a dedicated HES or hardware enforced security subsystem that is away from the application subsystem, which provides some of the fundamental secure services like secure boot, attestation, etc. So that is where one of these primary deployments come from. TPM is quite not an ideal solution in that scenario because TPM is a very targeted solution, whereas the HES that ARM-CCA defines is required to be a bit flexible, where it has to provide various services. There are performance requirements as well around crypto offloading and things like that. So that's where RSE is primarily targeted as a root of trust service. So now let's look at under the hood of the RSE from a hardware perspective. As I said in the beginning, it's a Cortex-M based subsystem. If you're familiar with the Corestone IoT designs that ARM publishes, this is based on the Corestone SSE 300 subsystem. It has got a Cortex-M55 as the CPU. But for RSE, there are several security components that has been added around the Corestone subsystem as part of the hardening process. So if we very quickly look at some of the hardware components that has been added on top of the standard design, there's the address translation unit, which allows RSE to be attached to a bigger 64-bit SOC. So it does the 32 to 64-bit translations. There's a security alarm manager, which you can consider as a special purpose security interrupt handler. So if there is any fault that any parts of RSE detects, SAM can go and reset the CPU and take actions when it detects faults that's coming from different peripherals. There's a key management unit, quite critical for the crypto operations for RSE. What it does is it creates a exclusive or a dedicated crypto flow for RSE. So the keys, especially symmetric keys that are stored in the RSE OTP, that can be loaded through the LCM or the lifecycle manager to the KMU, which then can be directly loaded to the crypto accelerator as well. So what that means is that crypto keys, when they traverse, they're not touching the system bus. And what that translates to is the RSE firmware never gets exposed to these keys ever in its life cycle, which is quite important from a defense in depth mechanism, which means that you don't inherently have to trust RSE firmware from sort of getting exposed or it getting access to some of these high value keys as well. What else? There is TRAM, which is basically doing encryption for the tightly coupled memory at the top. Then there's a crypto accelerator. So on an ARM-based solution, of course, it's a CryptoCell 315, but our partners can replace it with another crypto accelerator. But from an RSE design threat model standpoint, the crypto accelerator is a mandatory component because that is what brings the side channel protection when you're doing cryptographic operations as well. So quite an important component there. Then there's the interesting secure instruction cache. So this is also quite critical and quite interesting as well. What it does is it allows RSE to load firmware from an external flash, which is inherently untrusted, and the secure I cache is able to decrypt and execute in place as well. So what that means is you can have a tiny secure I cache, which might not hold the entire RSE code, but the RSE code itself will be in an external flash, which can be loaded, decrypted on the fly, and executed in place as well. So again, good for security, lower memory requirements. etc. Of course, there are a few other things around safety hardening. So RSE primarily has got a dual CPU lockstep CPU design. It has got ECC on all the non-volatile memories. It has got parity on all the buses, things like that. So quite a secure solution, starting with a basic IoT system design. So that is a very brief overview about the hardware aspects of RSE. Now, as sort of software people, let's look at what is the software story here. So when RSE was starting to get created, we already had Trusted Firmware M as a project. Some of you might know TFM as the secure processing environment for Cortex-M CPUs, which has got Trust Zone in it. So TFM as an open source project, which provides the PSA reference implementation, already runs on a Cortex-M CPUs. It provides the separation between normal world and secure world through Trust Zone hardware. It already had a secure partition manager, which is a lightweight kernel on the secure side with some standard secure services running on top of it, which could be accessed from the normal world through PSA APIs. Then it had the MCU boot-based BL2 bootloader that would authenticate the normal world and secure side images. So all these things already existed in TFM. So it was a matter of looking at how we could use such a well-written, secure piece of firmware on this new piece of RSE hardware, which has got some additional security requirements. So that's where we have kind of used TFM as the foundation, reusing all the TFM framework, all the isolation methodology that already exists in TFM. And we've picked up the secure partition manager, some of the secure services like crypto attestation, we have just reused it from TFM. Things like secure storage for the time being doesn't exist in an RSE version of firmware because on a bigger SoC, unlike microcontrollers, it's very rare you would have a on-chip flash. So secure storage is not required as a service. But there are other things we have reused. For example, TFM provides this facility to have an isolation in the secure world where you can separate out certain services from the key RSE services. What that means is the communication interface through mailbox or a trust zone agent is separated out from these critical services. What that means is that for these kind of secure enclaves, normally these communication drivers that usually is the target for an exploitation, but at least it's isolated from some of these key services as well. What else? So as part of RSE, we have also introduced 2 new bootloaders. So for the MCU-based TFM implementation, we just had BL2 and the TFM runtime. So over the last year or so, we have introduced the 2-stage bootloaders as well as part of the RSE builds. And there is the measured boot service as well, which Rafe will touch on later on in the presentation. So again, the story here is it's mainly TFM based, but there has been additional enhancements, new services, etc. that has been added to meet the RSE security requirements. So as I said, one of the new capabilities that we have added is the 2-stage bootloaders. So typically in a microcontroller, when TFM is deployed, the microcontroller would have a inbuilt bootloader. But in the case of RSE, we've created the BL11 and BL12. So BL11 is typically aimed at the ROM. So it is baked into the silicon, so it's quite critical. It's expensive if we have bugs, of course, in a ROM-based bootloader as well. So we've designed it in such a way that it's very tiny. It doesn't have a lot of capabilities. What it basically does is when the entire SoC comes up, it will be the first thing that comes up in the system. Its basic functionality is to authenticate and load this next stage bootloader, which is the BL12, and do some basic provisioning stuff as well. BL12 is more interesting in terms of capabilities. That's where the actual bootloader functionality resides. So it has got things like flash drivers so that it can load the next stage of bootloaders. It has got RSE to RSE communication. So if you imagine a bigger SoC, there might be multiple RSEs that is running on a bigger SoC as multiple routes of trust, and you want these RSEs to communicate. Then interestingly, BL12 authenticates BL2 using a PQC algorithm as well. So this is, I'll touch on it in the next slide. So this is something we've done in RSE as a future proofing exercise to bring in some PQC-based authentication at this stage where people are actively looking to move to PQC-based algorithms. As I said, BL1 basically based on ROM, so quite expensive. There are hardware, software problems, whereas BL12 is residing in OTP and an area in ROM which is patchable. So it's less expensive if there are fixes that we have to do after tape out. So this is where if there are problems in BL2, you can reprovision on a new chip an updated BL12. You're able to patch part of the ROM by copying the code to the RAM as well. So more flexibility, thereby there are more capabilities as well. So before I pass it on to Rafe, just a quick mention of the PQC work that has happened. So as I said, it is kind of not at a point in RSE where the entire boot flow is PQC based, but at least what we have done is the BL12 authenticates BL2, which is an MCU based bootloader using PQC, and we have gone with the LMS, which is a stateful hash algorithm, because when we started this effort, NIST was still trying to finalize the NIST algorithm, NIST approved PQC algorithms. Luckily, LMS is also now an approved algorithm. So it's a stateful hash signature algorithm that we have implemented in Mbed TLS and is upstream. So that gets pulled in for authenticating the images. It's not a drop-in replacement to ECDSA because it's got a limitation in the sense that you can only generate 1024 keys, signatures using a single key, which won't work if you're trying to use this algorithm for a runtime image because you might have more updates over the lifetime of the product. Whereas for something like a BL2, you might only have a limited update of the image over its lifetime. So for the time being, we are using BL2. There are plans to, of course, move to an entire PQC-based boot flow. So I think with that, I'll pass it on to Rafe to talk about some of the interesting features that he has been working on.
Yeah, so that was the state of RSE as of, what, 4 years ago now when we started? And since then, we've done all those features in terms of implementations, and what's happened is that RSE is now basically being shipped into everything. So we've got lots of integrations into the ARM compute subsystems, and because of that, we're starting to get partners designing products with RSE. And from this, it turns out that our initial assumptions about what the RSE was supposed to be doing are mostly incorrect. So we've had a few places where we've had to make changes, attestation, provisioning, and the PQC boot. So in attestation, we started off with a PSA attestation. So if you hear Tamash's talk, this is basically the short version of that, because all of the attestation is being implemented inside RSE. We started with PSA attestation, and then because the RSE is the CCA-HES, we then had the CCA attestation. It turns out there's a problem with that, is that the CCA attestation it's time-bounded. So when you create a Realm VM, it needs to get an attestation certificate. And if you start, the high-performance A-class cores can create, what, hundreds of VMs in a second, I think, were the numbers we were considering. And the RSE, we actually still don't know how performant it is. We're still waiting on some cycle-accurate testing on this, but we're pretty sure the performance is not that great. So this ended up being changed to delegated attestation. This is a scheme where effectively the RSE signs a public key and then passes that public key off to the RMM, and then the RMM can use that to service the CC attestation in much better time bounds. And the RSE basically just does this once and then goes back to sleep. So that worked quite nicely, although then we'd ended up with, we're up to 3 attestation partitions now, because we did finish CC attestation before delegated attestation turned up. And then we started seeing this requirement for DICE and the DICE protection environment, which we have another partition for that now. And then we're now being asked for SPDM attestation, and we're going to end up with another partition for that. So we're up to 5 attestation partitions. And we're also starting to be asked for having multiple of these at the same time. So, for example, we might end up doing PSA attestation and DICE attestation at the same time, which actually turns out to be not too bad. One of the things we have done is we've abstracted out. So originally, attestation partition was, it did basically the whole stack. So it collected all the measurements from the RSE boot up, and then it created certificates. And we realized quite quickly that wasn't going to work, because when you have multiple attestation partitions, you can't be duplicating all the logic together, all the measurements. So we've separated this into a measured boot partition, which has two purposes. It picks up all the measurements of the RSE bootloaders, and then it also allows the input of boot measurements from other system components. So the TFA bootloaders will now submit measurements to the RSE via that. And the thing with this is that it allows us to have multiple attestation partitions, which then just call into the measure boot partition and ask what are the measurements that I need to sign, which works quite nicely, really, because then we don't have to do any of the formatting. We can just basically plug all of them into the measure boot partition. The problem is that we're now starting to be asked about TPMs. And there was some talk, been some good talks earlier about firmware TPMs. We're also looking at discrete TPMs in the RSE, so that's where you would have a discrete TPM plugged into the RSE, or indeed on the main system bus, and then you would make TPM calls into the RSE, and then it would store the measurements in the TPM. And there's questions here like, what happens if we need to mirror these measurements? So for example, if you make a call into the measured boot service, does that go to the TPM as well? How do we keep these two in sync? And then there's another question going on about FTPMs in RSE. And so this sort of looks like it makes sense, right? We've got a relatively high security environment, certainly higher security than the secure side of the AP. But the problem turns out to be storage again. So the RSE being a firmware TPM means it has to have somewhere to do non-volatile storage, and because of the problems with internal flash, so usually the chips that are including RSE are on sort of 3 nanometer process nodes, you can't get internal flash on that size. So we don't have any non-volatile storage inside the RSE. You can use these cryptographically bound RPMC flashes, but we've had a lot of pushback on including those because no one wants to pay for it. So that's sort of where we are in the FTPM. We think it's possible. It'll probably end up looking a lot like the other FTPM implementation for Opti, but it requires hardware. So we're still sort of seeing how much appetite there is for that. The other thing that's changed a lot was provisioning. So originally provisioning, we designed this sort of very simple system. You had a debugger that would connect to the RSE. It would drop in a data blob with a signature, and then you would have some code that runs in the RSE ROM to unpack it and put into the OTP. The problems we had with this, firstly, the problem with this is that we then need to know what data we're provisioning into each system, and it became quickly clear that there was no way that was going to be standardized across the different use cases for the RSE. So the thing we decided to do here was to move the code that provisions the data out into a blob. So instead we ship this blob of code plus data into the RSE, and then it executes it. This is a bit more dangerous because, of course, we're letting the RSE run untrusted code, so we've got to be very careful about the authentication here. But it turns out to be really flexible, so we can accommodate very last-minute changes so very, very large changes to how the provisioning is required to work just by changing this blob. And it really decreases the surface area of the ROM because all you need is the loading logic, and then whatever you want to do afterwards all goes into the blob. And we found some other use cases of this as well. So for example, ADAC authenticated debug is one of the standards for allowing debugging without effectively having backdoors. We can't put ADAC into the ROM, it's too much code size, it's too dangerous, but we can put the ADAC logic into a blob and then have that blob contain a driver for the SDC600 debug channel, and then it can just run the full ADAC runtime, and we don't have to worry at all about security patches because we can just issue new versions of this. We can basically just rewrite this until we're happy with it. And the other thing that we came across was that we've made this assumption that the RSE would always have debug enabled, and the answer turns out this possibly isn't true. There's questions about grey market protection, where you effectively want to limit what is allowed to be run on the chip so that the factory doesn't overproduce them and then sell them off on the side. That basically requires locking down the RSE debug and making it so that it can only run authenticated code even from the very beginning. And then there are also places where you might not want to allow access to the RSE in the DM lifecycle states, because at that point there are some secrets in the device. So in both of these cases, the solution was to add this DCSU messaging peripheral. So this allows us to have a a channel directly into the RSE subsystem from the outside. It's accessed via the debug path. Effectively, it ends up being this sort of bridge which is exposed even when the debugger's closed. And it gives us a sort of four-word FIFO, and we've built a communication protocol on top of that. But crucially, that means we can close the RSE debug, and now all the provisioning flows all use the DCSU. Where are we? The other things that have been going on are to do with PQC again. So since then, quite recently actually, NIST have issued some more PQC guidance, which they've decided to deprecate RSA and ECDSA in 2030 and ban them in 2035. So this has basically made everyone panic. The RSE, we planned for this, we can do this upgrade to PQC, but if you look at this, it means that basically every part of the system does any bootloading, because it's bootloading where this ban's been implemented, has to suddenly have implementations of MLDSA. And the new PQ algorithms are not more efficient than their predecessors. They tend to use quite a lot more memory in particular. And so one of the things we were considering was, what if the RSE could do more of the system bootloading? Because then it's very simple. We over-provision just the RSE, and then everything else just calls into it to do bootloading. And you get some nice benefits out of this. You can get rid of loads of bootloaders from the system. You get much better fault injection resistance from the RSE because it does all the copies. So it's no longer you just sort of zap the chip while it's copying the bootloader, and then you can run whatever code you like. The RSE is very resistant to that. It will generally panic if that happens, and eventually decide to just brick itself if you keep doing it too often. And it means that we've got to do a post-conflict update in only one place, which makes our life a lot easier. So this has got a lot of traction. People like the look of this, although the devil's in the details, because of course if the RSE is doing system bootloading, then you've got to work out what sorts of image formats it's using, and you've got to make that percolate all over the system. So this has proved to be quite difficult, and it's got a lot of parties inside, but we are making some progress. And the other thing with the PQC, I said we've got this post-quantum upgrade path. It turns out that's not gone as well as we thought. LMS looks really good, but the problem is ops teams really hate it, and it's because you can't back up the private keys. So if you want to back up a key, and you do because this is your sort of main device key, if you lose this, then you can't do any more provisioning. You need to have an entirely separate HSM and have a different key on the HSM. You need to sort of have 3 or 4 of these spread all over the country, whereas otherwise you would just have sort of encrypted USB sticks with the keys wrapped by the HSM. So there are options to do things that look a bit like backing up keys, but they are not good. And the feedback we've had basically is that LMS is a non-starter because of this. Interestingly, we started to see this go a bit the other way again, now that people are sort of panicking more about the NIST guidance. So we'll see how that goes, but the feedback we've had basically is you need MLDSA. So we're working on an MLDSA implementation. Performance, again, is a concern. The RSE isn't very fast. It looks like potentially MVE could be helpful here. It's interestingly looking like the performance is actually quite similar to ECDSA at the moment from the first numbers we've got back, which is very promising. But that's a very hardened ECDSA implementation versus potentially less hardened MLDSA implementation. So we'll have to see how that goes in future. And then, yeah, so in future we might be looking at hardware acceleration for MLDSA in the RSE, which would be very good. And then the other problem we've had is that provisioning based on the RTL key has been difficult. It turns out that keeping a key secret while putting it into the RTL and handing that RTL to someone to go and build the chip is very difficult, especially because the provisioning is happening inside the fab. You're sort of handing the key. You've got to prevent the fab getting hold of the key. So we've had some issues with doing that. So the initial plan of using this symmetric key in the RTL to do the provisioning has also not panned out. So we've ended up with a full ECDSA validation driver in the ROM, which we didn't want to do, but we've managed to go through quite a lot of testing for that. We're pretty sure it's okay. And this means that at least if you do manage to get hold of the RTL key, you can't provision anything. You do need the RTL key still for encryption. If you want to provision secrets, there's no way around that really. You need a device class key to do the encryption. And then what's next? So basically, we've got a lot of work areas going on. We've got the RSE-centric boot flow, discussions happening around that. We've got the MLDSA work. We've got the RSE as an FTPM. That's looking very interesting considering all the talks we've had here. We've got Tamash's attestation partitions that we need to do. The safety critical use case is quite interesting. All the hardware in the RSE actually it's got the hardware it needs to do safety critical, to run safety critically. The problem is the software. So we're sort of assessing how much software change we would need for that to happen. And I worry that the answer is a lot. It would be good to have on the RSE, and it would allow us to have better use cases in automotive, for example. We are getting a new hardware revision sometime soon. This sort of fixes some of the issues we've seen around provisioning, and it has moved some of the crypto into the RSE, which is nice because now it was very hard to write code where you don't know what crypto accelerators you're going to have. And so now the RSE has some standardized crypto inside. That's going to make our life a lot easier. And eventually, we'd like to get PSA certified once we have some silicon. Yeah, I think that's everything. Questions?
You use the term partitions for the different kind of usage context.
Yep.
What is encompassed in a partition?
It's effectively, it's sort of like the operating system program, except the program is it's a very simple sort of IPC handler with a couple of entry points. So it would normally basically look like a thing that you can call into as a function. Say for the crypto, you call into something with some pointers, and it encrypts it. It performs encryption. And the main thing that's useful there is that because they exist as sort of processes, it means we can isolate them from each other. So we've got really good.
So TA, basically individual trusted apps, basically.
Yeah, basically.
Okay. And so each one's like that code, then calling the other attributes that it.
Yeah, through a IPC FFM interface. Yeah.
So by partitions, you actually mean a TA.
Yeah.
Yeah.
Case use one pipe, we use the FFM interface. Yeah.
Can you talk a little bit more about some of the safety cases you're looking at? Are you looking at more like isolations and things like that, or something else?
Well, I think, so the main thing about the RSE at the moment is we make no guarantees at all about availability. So in our threat model, we say if the RSE just gives up, that's not our problem. We're perfectly happy with that. And of course, in the safety use case, people tend to get quite upset if you say that. Yeah. So we're looking at things like trying to make sure the RSE is more available. We use the watchdogs to make sure that all of our processes are actually finishing, and we need to basically go and talk more to the automotive teams about what they want from the RSE, because this is a domain we don't understand, so we need a lot of feedback to say whether we can do it.
Perfect, thanks.
Any other questions?
Not necessarily a question, but a comment here. Availability is becoming just as important in the data center as it is in automotive, because you're putting these devices in these incredibly tough environments. Sometimes they're going to be dipped in coolant, or they're going to have a lot of things going on. And if key things like this start failing, then it could actually cause conditions that are unfavorable. So what we're seeing is a lot more availability issues, even in data center, having to have some run to completion assurance, or basically availability.
Yeah, it's something that would be very interesting to look at, because, like you say, it's effectively all upside, and we've already got the hardware for this. We've already got the ECC. The ECC at least is working. It's the cases where you have sort of the dual core lock step, where the only thing we can do is sort of panic. And at the moment, panic means shut down the RSE, shut down the whole system. And if we could make that work a bit more reasonably, where maybe we just reset part of the RSE instead and try and come back up, then I think that would be a lot more palatable.
Yeah, hopefully that's a RAS story to RSE as well.
Yeah. And I think that's all of our time.